Well, what a stir. The importance of realising that the Earth drops at a given rate on a globe Earth cannot be overestimated. All the evidence is there if you have a mind to look. And the scientists and globe Earthers have kittens when simple evidence comes to the fore. Remember Occam's razor? Where the simplest reason is usually the correct one. Well, we see a long distance because it's flat. And as the meerkats say in the British advert, simples. But no. What a stir and weather storm was created when a picture by Joshua Nowicki was shown on a prime-time American weather slot. Joshua had taken a photograph of the Chicago, Illinois skyline from Grandmere Park, Michigan, 57 statute miles away. You see, Wikipedia states that Lake Michigan is 577 feet above mean sea level and that Grandmere Park is 587 feet, a mere 10 feet difference. Although in Edward Hendry's book he states that Grandmere Park is 600 feet. We will use this to be on the safer side. So this means that Grandmere Park is 23 feet above Lake Michigan. I state this because I have seen some people claim in debunking this that there is a difference of 230 feet. They are wrong. If we were to suppose he took the photo standing up, that would have added a maximum of, let's say, 6 feet, though it was probably far less. That makes 29 feet above Lake Michigan. At 29 feet, the geometric horizon would be less than 7 miles away. In the Earth curve calculator illustration, putting in 29 feet and a target distance of 57 miles, it shows that the eye reaches a geometric horizon at 6.59 miles and that the drop, or hidden target height, is in fact 1,694 feet. However, using a distance to the geometric horizon rounded to 7 miles, the drop due to curvature of the Earth using the remaining 50 miles is 8 times 50 squared divided by 12, which is equal to 1,667 feet. Now the street level of Chicago is 23 feet above Lake Michigan, so the street level should have been 1,644 feet below the horizon. Now the tallest building in the picture was Sears Tower, now renamed Willis Tower. It is 1,450 feet above street level, and including the street height of 23 feet, is 1,473 feet above Lake Michigan. And with the antennas on top of the tower, this brings the total height up to 1,729 feet above Lake Michigan. This means that none of the buildings in Chicago should have been visible, and what would have been left of the tower building should have been 194 feet, plus of course all those aerials. But the photograph clearly does not show this. In fact, not only can the entire tower be seen, but also all the other buildings along the shore of Chicago. The photograph clearly demonstrates that the Earth is flat. So the weatherman on ABC News, Tom Coombs, tried to brush it aside by stating that Chicago's skyline isn't really there, but that this is an example of a superior mirage. However, the problem with this is that a superior mirage of an object is usually inverted above the actual object. See these examples. What would a superior mirage of the Chicago skyline look like? Well, we have such a picture taken from the western shore of Michigan in St. Joseph by J. Michael Hall on April the 18th, 2015. Notice the towers are upside down. A further problem for globe earthers is that we can repeat the experiment ourselves. No sophisticated equipment needed. It is testable and repeatable. This is the true scientific method. Rob Skiba and Rick Hummer repeated and confirmed the results in June 2016. They chartered a boat and were able to see the Chicago skyline from the mouth of the New Buffalo Harbor, a distance of 42 miles. And they further confirmed that the Chicago skyline was not a mirage by travelling the entire length of Lake Michigan from the shore of New Buffalo Harbor to within approximately 9 miles of Chicago. At all times, the Chicago skyline remained upright, and this confirmed that indeed, starting at 42 miles out, this was not a mirage. You can follow the journey on YouTube. Now, I'd like to show you the general calculation of distance to the horizon on a curved surface. It ends up with a very well-known formula known in flat Earth, and that is the drop is 8 inches per mile squared. And this is a very good approximation that works out very good, at least up to a distance d of 500 miles. Of course, eventually it ends up with a vertical drop, but up to 500 miles, 8 inches per mile squared works out very well. And I'm just going to show you the mathematics of it. So, if you're turned off, just fast forward a little bit. But I want to show you it because 8 inches per mile squared is going to be used for an awful lot of things. And as soon as you realise what that means, you can go out into the countryside yourself and immediately show that you can see far beyond this calculated distance, and therefore show to yourself that you can't be on a globe as you are told. Now I'd like to show you the general calculation of distance to the horizon on a curved surface. So here we have a diagrammatic representation of the Earth, with the centre being C, the radius of the Earth represented by R. Here is the observer O, and H then is the height of the observer above the surface of the Earth, and the observer looks across again to where his horizon line touches the Earth, and we're back to then G being the geometric horizon. This comes from Pythagoras, where a squared plus b squared equals c squared for a right-angled triangle. So just writing this out, c squared is r plus h. So you've got r plus h squared is equal to r squared and d squared. R squared plus d squared. And this r plus h squared can be rewritten, quadratic equation, r squared plus 2rh plus h squared is equal to r squared plus d squared. So having got that far and expanded the r plus h term, we can now take r squared from both sides. So if we take r squared off at both sides, we've got 2rh plus h squared is equal to d squared. Now, RH, R here is the radius of the Earth, which is 3,963 miles, and H is just a few feet, 500 feet, 10 feet, even 1,000 feet, but it's H squared, so 1,000 feet squared is nothing like the R of 3,963. Therefore, to simplify the equation, and again this is only approximation, but it's a very close approximation, but this H squared term is going to be so small and insignificant that we can ignore it, and we can simplify the equation to being 2RH equals d squared. And to find H, we just divide this by 2R. So H equals d squared divided by 2R. We can work this all out because R equals 3,963 statute miles. So H equals 1 over 2 times this, 7,926 times d squared. So this means that H equals 0.0000126,167,0452 times d squared, which is in statute miles. And if we want to convert from statute miles to inches, then we multiply by 1,760 to get it into yards, by 3 to get it into feet, and by 12 to get it into inches. So this then means that H equals 8 times d squared, which is in inches, and that's our equation. So for example, if d equals 10 statute miles, then H equals 8 times 10 squared in inches, which equals 8 times 100 inches, which equals 800 inches. And to get this into feet, then we divide by 12, and 800 divided by 12 equals 66.6 feet. I have shown you the geometric construction method of coming up with 8 inches per mile squared. There are other methods, and for completeness I'll show you this using the trigonometry formula, but as you can compare one to the other, they come up with almost the same figure.